Section 5.4, page 3. So we just defined the average value of a function, but didn't write it all together. So here it is written out together. If I have f, which is a continuous function on the interval from a to b, then I can integrate that function from a to b. And if I take that integrated value and multiply it by the reciprocal of the interval width, then I essentially have the average function's output. Okay, that's a lot going on. So here's what we're going to do. We're going to break it down. Now, we've already talked about the mean value theorem, where we're referring to a value c that exists that has a parallel tangent line to the endpoints of the function a and b. That's just generic in terms of a function. But now, when we talk about the mean value theorem, we can also refer to a separate formula for integrals. So in a sense, think of this ant farm off to the left. There are certain areas where there's a lot more paths that the ants have gone through, and then there's sections where maybe no ant path exists. That's hard to say. But what happens is, what if we could even this out? If this represents a whole bunch of ants live on the left and no ants live in this sliver over here, what if we told the ants they all had to live somewhere evenly dispersed? So we can only have the same number of ants in each section of this ant farm. That's essentially what the mean value theorem for integrals is doing. Now, we know an integral can give us the area under the curve from an interval a to b. But that same interval, if we had had a uniform height, not a varying height, then there would be area under that curve from the same interval, and these two need to be equal. So for example, I've got this curve over here, and we could shade everything below the curve between some a and b values, or there's going to be some number c in the middle, not dead center in the middle, but somewhere between a and b. I haven't really defined those, where if we had this constant height, we could then turn this into a rectangle where we could find that area. And the height of the rectangle is the output of the average function for that value c. Putting some of that into words, f is that continuous function on the closed interval from a to b. There is some number that is inside of a to b. You should always double check that, make sure you haven't made a mistake, such that the average function is equal to that integral over that range, and this gives us f of c. So here's what's happening. I've got this integral, and it's going to give me area under the curve. But notice, if I took this formula off to the left, and if I multiplied both sides by the distance of the interval, then what I've done is I've created the height for the average function value, and by taking the distance across the bottom, the interval range, I've created that rectangle. I now know the width and length of my rectangle, and I can find that area much easier than the area under the curve. But yes and no, let's keep going. So I'm asked to find f average, so this is kind of like part A, for a given function on my closed interval. And part B, I'm asked to find what is that value c, such that c gives me that particular output. And we'll go ahead and visualize this off to the right once we get there. So I've got this function f of x equals the square root of x. And I'm integrating it from 0 to 4. But if I want the average, I then need to multiply by the reciprocal of the width, so taking b minus a, and so 4 minus 0 is just 4. So I'm ready to integrate, where I take my x to the 1/2, I add 1 to the exponent in the disguised form of denominator over denominator to give me like fraction, so I can add to get 3/2. And instead of dividing by 3/2, remember we multiply by the reciprocal. And I'm going to evaluate this from 0 to 4. So f of b minus f of a. Well, since 0 is my a value, this whole right term is going to drop off to be 0, and I really only need to focus over here. When I have 4 to the 3/2, remember I can write it as the 1/2 power of 4, or the square root of 4 to the cubed power. So I'm going to go ahead and know that the square root of 4 is just 2, that I'm going to need to cube, so I'll write it 3 times. The 2 in my numerator can cancel with the 4 in the denominator, and now that I actually have a 2 in the denominator, can cancel with one of those numerators. So I'm going to have 4/3. The output height of my average function is 4/3 or 1 1/3. So I kind of drew this line here. I didn't necessarily pinpoint at first that, remember, we're going from 0 to 4. So from 0 to 4, I have this rectangle where I know the width, 4 units, and I know the height, 1 1/3. So I could find the area under the curve, but we weren't really asked to find that. We were just asked to find the F average value. Now, the other piece is, what if we're asked to find C? Where does C occur? I didn't necessarily need it because I found the area under the curve without C, but it might be helpful to know what C is. Using the fact that F of C gives us that output average, I've got my F function, which is a square root. What number do I plug in to get 4/3 out? Well, I'm going to solve this by squaring both sides to get rid of the square root. That will give me 16/9. And now I have found that C is 1 7/9 if I wasn't going for a decimal value. And yeah, if I'm going from 0 to 4, then check. C is in between that range. And following up with that illustration, I had already shown you the rectangle, remembering that the shape of a square root starts here at 0, because we're not going to take negatives, and comes up, kind of rounded off to the right. Well, if we're going from 0 to 4, I'm going to take that shape, and in light blue, I shaded in this area, and I've got some area that we haven't actually defined, although we could turn around and multiply this to see that it's 16/3, which, yeah. So what happens is, I wanted to visually show you, notice the rectangle has this part that's not under our curve, but keep in mind our curve also had some area that's not in a rectangle, and that's kind of where they balance each other off. You could almost even think of one piece kind of picking up and flipping into another to fill in the space. But all we're going to say is, hey, if I had to integrate f of x, which is a square root of x, from 0 to 4, I could find that area by integrating from 0 to 4, getting the actual area of the curve, and then if I needed to know what the height of the rectangle was, not just the area of the curve, then I would know what that height is, and the width was already given.